Now in this lecture we'll find out the radius of the small circle. In the drawing we have a quarter circle, A or B is a quarter circle. We know that side OB equals to 6 units in itself, that is to say the radius of this quarter circle equals to 16 units. In addition, you know that inside this quarter circle AOB we have this semicircle and also this circle, and our mission is to find out the radius of this circle, or in other words, our mission is to find out the value of R, that is the radius of this small circle. So, first of all, we define the relevant points to this question with letters. We define the center of this semicircle, this point, as point P. Likewise, we define the center of this small circle, this point, as point Q. We define the point of tendency obtained at OB with this circle, this point, as point M. We define the touching point of this semicircle with this small circle, this point is point S. And finally, we define the point of tendency of the touching point of this small circle with this big quarter circle, this point is point T. And we know that AOB is a quarter circle, therefore this angle AOB must be equal to 90 degrees in its size. So this angle equals to 90 degrees in its size, because AOB is a quarter circle. So here we can implement rule 1 in our drawing. According to rule 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So, in the drawing we have a circle, and this is tangent AB, that is tangent to this circle is point M. Point M is the point of tendency of tangent AB with this circle. And we have the radius OM that is equal to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule, rule 1. We can actually implement rule 1 in our drawing. In our drawing, we have the radius OM that is equal to R. The radius OM is drawn to point M, that is the point of tendency of tangent OB with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent OB will be perpendicular to the radius MO. If OB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, we'll do a construction, that is to say from point Q, we'll do perpendicular on AO. Again, from point Q, that is the center of this small circle, we'll draw perpendicular on AO. So okay, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and side AO, this point is point H. By doing this construction, get the quadrilateral HQMO. Inside this quadrilateral HQMO, we have 1, 2, 3 right angles. the sum of three right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral HQMO, we have four right angles, and according to rule 6, any quadrilateral that has four right angles must be at least a rectangle if not a square. So you relate to this quadrilateral HQMO as a rectangle because it has four right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle HQMO, side QM must be equal to the opposite side HO. But QM equals to R, therefore HO must be also equal to R. So we know that HO equals to R, PO. So first of all, we know that point P is the center of this semicircle, and the radius of the quarter circle that is equal to 16 units in its length, according to what is given as the question, is also the diameter of this semicircle. So the diameter of this semicircle AO equals to 16 units in its length. And therefore, the radius of the semicircle must be equal to half of it. That is to say, the radius must be equal to 16 over 2, that is 8. So the radius AP of this semicircle equals to 8 units in its length. And the radius PO must be also equal to X units, 8 units in its length, because this is half of the diameter, that is 16 units. So we know that PO equals to 8 units in its length, AO equals to R. What is the length of PH? PH equals to PO minus HO. Again, PH equals to PO minus HO. So I write it down. PO, actually PH, this line 7 PH is equals to PO minus HO. So PH equals to PO. PO is 8, it is the radius of the semicircle, that is equals to 8 units in its length, minus HO. Just write down for now that HO equals to R. So in total, PH equals to 8 minus R units in its length. PH equals to 8 minus R units in its length. This semicircle touches this small circle at point S. Point S is the touching point of this semicircle with this small circle. So here you can say that the semicircle has an internal notch, an external notch with this small circle. Again, the semicircle have an external notch with this small circle. That is to say, it touches the small circle externally at point S. And whenever we have an external notch between two circles, you can implement rule 10. We'll take rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together passes for their touching point. So in the drawing you have two circles. Those two circles touch each other externally at point P. Point P is the touching point of those two circles. The center of this circle is 0 at point O. The center of this circle is 0 at point M. And the thread line that connects their centers together is of course the thread line OM. According to this rule 10, the thread line OM must pass through point P. Again, the thread line OM must pass through point P, or OPM is one thread line. Again, according to rule 10, OPM is one thread line. So we can actually implement rule 10 in our drawing. One, because in our drawing, as I mentioned before, this semicircle have an external arch between this circle. That is to say, it touches this small circle at point S. So they have the semicircle and the small circle have an external arch between them at point S. Therefore, we can implement the rule 10. According to rule 10, we know that the center of this semicircle is there at point P. The center of this small circle is there at point Q. And the thread line that connects their centers together is the thread line PQ. According to rule 10, the thread line PQ must pass from point S, that is their touching point. Again, the thread line PQ must pass from point S, that is their touching point. That is to say, PSQ is one straight line. Again, PSQ is one straight line. So we can rejoin points P and Q together by straight line, and according to rule 10, the straight line PQ must pass from point S. So the third line PQ that connects the centers of the semicircle and the small circle together passes from point S, that is their touching point. What is the definition of line 7 PS? Line 7 PS starts from point P, that is the center of this semicircle, and ends at point S, that is the point of the semicircle itself. So this is exactly the definition of a radius. Therefore, PS is the radius of the semicircle that is equal to 8 units in its length. What is the definition of line segment QS? Line segment QS starts from point Q, that is the center of the small circle, and ends at point S, that is the point of the small circle itself. So this is exactly the definition of a radius. Therefore, QS is the radius of the small circle that is equal to R. R is the radius that we are looking for in this question. And because of the fact that according to rule 10, PSQ is one straight line, PSQ is one straight line, it means that PQ must be equal to PS plus SQ. Again, PQ must be equal to PS plus SQ. So I write it now. PQ must be equal to PS plus SQ. So PQ equals to PS, that is 8, plus SQ, that is R. So in total, PQ equals to S plus R. In the next step, I'll copy the green right triangle, the green upper right triangle PHQ in the new page, and we'll implement the Pythagoras theorem with this right green triangle, triangle PHQ. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the abbreviation for Pythagoras theorem. We already found out that PH, sine PH of the green triangle equals to H minus R. We just right now found out that the hypotenuse PQ equals to 8 plus R. So actually, this is the right triangle PHQ, the right green triangle PHQ is the commit from the original drawing. According to the Pythagoras theorem, in this right triangle PHQ, PQ square equals to PH square plus HQ square. Again, PQ square equals to PH square plus HQ square. So I write it down. So PQ square, that is the square of the hypotenuse of the right triangle PHQ, must be equal to PH square plus HQ square. PQ is 8 plus R, therefore PQ square is 8 plus R square, and it must be equal to PH square. PH is 8 minus R, therefore PH square is 8 minus R square, plus HQ square. HQ is the missing side, so we leave it as it is. So it is plus HQ square. So according to equation 1, we actually found out that 8 plus R square equals to 8 minus R square plus HQ square. Here we open the brackets on both sides of this equation, equation 1, and we get that according to this equation, equation 1, 8 plus R square equals to 8 squared, that is 64, plus R square, plus 2 times 8, that is 16, times R. So it is plus 16R. And it is equals to 8 minus R square. Actually, 8 minus R square equals to 8 squared, that is 64, plus R square, minus 2 times 8, that is minus 16, times R. So it is minus 16R. Plus HQ square. So here we have 64 on both sides of this equation, equation 1, so 64 will get cancelled. And we also have R square on both sides of this equation, equation 1, so R square also will get cancelled. After I cancel those two expressions, what is left from this equation, equation 1? In this side of this equation, equation 1, we left only with 16R. In the other side of this equation 1, we left with minus 16R plus HQ square. So according to equation 1, we actually found out that 16R equals to minus 16R plus HQ square. Here we add 16R to this equation, equation 1, and we get that according to this equation, equation 1, 16R plus 16R is 32R equals to HQ square. Here we substitute 32 by 16 times 2, and we get that 32R is 16 times 2R equals to HQ square. Here we take a root out of this equation, equation 1, and we get that HQ equals to the square root of 16, that is 4, times the square root of 2R. So inside the root we left only with 2R. So in conclusion, we found out that HQ equals to 4 times square root of 2R. So okay, this is side HQ, that is equals to 4 times square root of 2R. But we already found out that quadrilateral HQMO is a rectangle, and we also know that the opposite sides of a rectangle are equal to each other. So in a rectangle HQMO, side HQ must be equal to the opposite side OM. But HQ equals to 4 times square root of 2R, therefore OM must be also equal to 4 times square root of 2R. So we have here the small circle touches the big quarter circle at this point. Repeat again, the touching point of this small circle with the big quarter circle is here at point T. That is to say, the small circle have an internal notch with the big quarter circle. Of those two circles touch each other internally at point T. They have an internal notch between them at point T. And whenever you have two circles with an internal notch between them, you can implement rule 9. I'll take quickly on rule 9. According to rule 9, if two circles touch each other internally, then the straight line that connects their centers together passes through their touching point. So, in the moment you have a big circle, the center of this big circle is 0.0. We have also this small circle, the center of this small circle is 0.m. According to this rule 9, the straight line that connects their centers together, that is to say the straight line OM, must pass through point P. Again, the straight line OM must pass through point P, that is their touching point. Or OMP is one straight line. Again, OMP is one straight line. Okay? You can definitely implement rule 9 in our drawing. Why? Because in our drawing, this small circle have an internal notch with this big quarter circle. That is to say, those two circles touch each other internally at point T. Therefore, we can implement here rule 9. Whenever you have an internal notch between two circles, you can implement rule 9. According to rule 9, we know that the center of the big quarter circle is here at point O. The center of this small circle is here at point Q. And the straight line that connects their centers together is the straight line OQ, and according to rule 9, the straight line OQ must pass for their touching point, that is point T. Again, the straight line OQ must pass for point T, that is their touching point. Or OQT is one straight line. Again, OQT is one straight line. So we join points O and Q together by straight line, and according to rule 9, the straight line OQ must pass for point T, or OQT is one straight line. From the drawing, you can see that the straight line OQ passes for point T, or OQT is one straight line. Okay, OQT is one straight line according to rule 9. But if OQT is one straight line, it means that OT is also one straight line. OT is one straight line. But what is actually the definition of the straight line OT? The straight line OT starts from point O, that is the center of this quarter circle, and ends at point T, that is the point of the quarter circle itself. So this is exactly the definition of a radius. Therefore, OT is the radius of this quarter circle, that is equal to 16 units in its length, according to what is given as the question. So can I know that OT equals to 16 units in its length, because it is the radius of the quarter circle. What is the definition of this line segment QT? Line segment QT starts from point Q, that is the center of this small circle, and ends at point T, that is the point of the small circle itself. So this is exactly the definition of a radius. Therefore, QT is the radius of this small circle, that is equal to R. And because of the fact that according to rule 9, OQT is one straight line, it means that OQ equals to OT minus QT. Again, OQ equals to OT minus QT. So write it down. OQ equals to OT minus QT. So OQ equals to OT. OT is 16 minus QT. We just write down that QT equals to R. So in total, OQ equals to 16 minus R. this line segment OQ equals to 16 minus R units in its length. In the next step, I'll copy the right blue triangle OMQ in a new page, and we implement the Pythagoras theorem on this right blue triangle OQM. We just found out that the hypotenuse OQ of the blue triangle equals to 16 minus R. We already found out that side OM equals to 4 times square root of 2R. And finally, side QM of the blue triangle equals to R. It is the radius of the small circle. Here by PT is the abbreviation for Pythagoras theorem. So actually, this is the right triangle OQM that I call it from the original domain, and repeat again that the hypotenuse OQ equals to 16 minus R, QM equals to R, it is the radius of the small circle, the radius that we are looking for in this question, and we already found out that side OM equals to 4 times square root of 2R. So according to the Pythagoras theorem, in this right triangle OQM, OQ squared, that is the square of the hypotenuse, equals to QM squared plus MO squared. So I write it down. This will be question 2. So OQ squared, that is the square of the hypotenuse, equals to QM squared plus OM squared. The hypotenuse OQ is 16 minus R, therefore OQ squared is 16 minus R squared, and it is equals to QM squared. QM is R, therefore QM squared is R squared plus OM squared. OM is 4 times square root of 2R, therefore OM squared is 4 times square root of 2R squared. So here we open the brackets on both sides of this equation 2, and again this goes into this equation 2. 16 minus R squared equals to 16 squared, that is 256, plus R squared, minus 2 times 16, that is minus 32 times R, so it is minus 32R, equals to R squared, and 4 times square root of 2R squared equals to 4 squared, that is 16, and square root of 2R squared equals to 2R. Why? Because the power cancels the root, and we left only with 2R. So according to equation 2, we have found out that 256 plus R squared minus 32R equals to R squared, and 16 times 2R is 32R. So here in this equation 2, we have r squared on both sides of this equation 2, so r squared will get cancelled. After cancelled r squared, on this side of equation 2 we left only with 256. On the other side of this equation 2, we left with 256 minus 42r. In the other side of this equation 2, we left only with 32r. So according to equation 2, 256 minus 32r equals to 32r. Here we get 32r to this equation 2, and you get that according to this equation 2, 256 equals to 32r plus 32r is 64r. 256 equals to 64r. Here we divide this equation 2 by 64. And you get that according to this equation 2, r the radius of this small circle, the radius that we are looking for, equals to 256 over 64 is 4. So if we found out that the radius of this small circle r equals to 4 units in its length. So in the next step, I'll summarize the lecture. In this lecture, I found out the radius of this small circle or the value of r. In the drawing, we have a quarter circle. A or B is a quarter circle. Inside this quarter circle, we have this semicircle. We know that AO equals to 16 units inside. That is to say, actually we know that the radius of this quarter circle equals to 16. Why? Because OB, actually we know that OB equals to 16, but because of the fact that AO and OB, they are both the radii of this quarter circle, AO must be equal to OB, and OB equals to 16, therefore AO must be also equal to 16 units in its length. AO must be also equal to 16 units in its length. It is also the radius of this quarter circle that is equal to 16 units. So in addition, we know that inside this quarter circle AOB we have this semicircle and this small circle, and we know that this small circle touches this semicircle at point S, and our mission is to find out the radius of this small circle, of the value of r. So in the first step, we defined the relevant points to this question with letters. We defined the center of this semicircle, this point as P. We defined the center of this small circle, this point as Q. We defined the point of tendency of tangent OB with this small circle as M. We defined the touching point of this small circle with this semicircle, this point as point S. And finally we defined the touching point of the big quarter circle with this small circle, this point as point T. AO equals to 16 units in its length because AO is the radius of the quarter circle. This is equal to 16 units. But AO is not only the radius of this quarter circle, but it is also the diameter of this semicircle. So we know that the diameter of this semicircle AO equals to 16, therefore the radius must be equal to half of it. That is to say 16 over 2 is 8. So the radius AP of this semicircle equals to 8 units in its length, and then radius PO also equals to 8 units in its length. It is half of the diameter. Okay. We also know that AOB is a quarter circle, therefore this angle AOB must be equal to 90 degrees in size. We implemented rule 1. According to rule 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. Here we have the radius QM of this small circle, R is the radius that we are looking for, so the radius R, that is QM, is drawn to point M, that is the point of tendency of tangent OB with this small circle. Whenever your radius that is drawn to the point of tendency, then tangent OB will be perpendicular to the radius MQ. If OB is perpendicular to MQ, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. In the next step, actually did a construction, that is to say from point Q, we do perpendicular on AO. Again, from point Q, we do perpendicular on AO. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and AO, this point is point H. By doing this construction, we created a quadrilateral HQMO. Inside this quadrilateral HQMO, we have 1, 2, 3 right angles. The sum of right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total it must be equal to 360 degrees according to the rule. Then the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore this fourth missing angle must be equal to 90 degrees in size. So inside quadrilateral HQMO, we have 4 right angles, and according to rule 6, any quadrilateral that has 4 right angles must be this rectangle if not a square. So in order to this quadrilateral HQMO is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle HQMO, side QM must be equal to the opposite side HO. But QM equals to R, therefore HO must be also equal to R. We know that PO equals to 8, HO equals to R, so what is the length of the missing side PH? From the drawing it is very easy to see that PH equals to PO minus HO. Again, PH equals to PO minus HO. PH equals to PO minus HO. So PH, this side PH, like segment PH equals to PO. PO is 8, it is the radius of the semicircle, it is equal to 8 units in its length, minus HO. We just right now found out that HO equals to R. So in total, PH equals to 8 minus R. This side segment PH equals to 8 minus R. From the drawing, it is very easy to see that this small circle touches this semicircle externally at point S. So the semicircle and the small circle have an external notch between them at point S. And whenever you have two circles with an external notch between them, you can implement rule 10. I'll repeat quickly on rule 10. According to rule 10, if two circles touch each other externally, then the third line that connects their centers together passes through their touching points. So in the drawing we have two circles. Those two circles touch each other externally at point P. Therefore they have external notch between them at point P. We know that the center of this circle is at point O. The center of this circle is at point N. The third line that connects their centers together is of course the third line OM, and according to this rule 10, the third line OM must pass through their touching point, that is point P. Again, the third line OM must pass through their touching point, that is point P. Or OPM is one side line. Again, OPM is one side line. We can actually implement rule 10 in our drawing. Why? Because in our drawing, again, the small circle touches this semicircle at point S. Therefore, they have an external notch between them at point S, and therefore, according to rule 10, we know that the center of this semicircle is at point P. Here, at point P, the center of this small circle is here at point Q. And according to rule 10, the third line that connects the centers together, that is to say the third line PQ, must pass through their touching point, that is point S. Or PSQ is one third line. Again, PSQ is one third line according to rule 10. Therefore, when we join points P and Q together by third line, we know that the third line PQ passes through point S. Why? Because PSQ is one third line. So what is the definition of line segment PS? Line segment PS starts from point P, that is the center of this semicircle, and ends at point S, that is the point of the semicircle itself. So this is exactly the definition of a radius. Therefore PS is the radius of this semicircle that is equal to 8 units in its length, according to what we already found out. What is the definition of line segment QS? Line segment QS starts from point Q, that is the center of this small circle, and ends at point S, that is the point on the small circle itself. So this is exactly the definition of a radius. Therefore, QS is the radius of this small circle that is equal to R. And because of the fact that according to rule 10, PSQ is one straight line, it means that PQ must be equal to PS plus SQ. Again, according to rule 10, PQ must be equal to PS plus SQ. Here, PQ must be equal to PS plus SQ. So PQ equals to PS, that is 8, plus QS, that is R. So in total, PQ equals to 8 plus R. This line segment PQ equals to 8 plus R, units in its length. You can see here, 8 plus R. In the next step, I copied the green right triangle PHQ in a new page and we implemented the Pythagoras theorem on this right triangle PHQ. This is the right triangle PHQ that I copied from the original drawing. We just right now found out that the hypotenuse PQ, this right triangle PHQ equals to 8 plus R. We have already found out that PH equals to 8 minus R, and HQ is the missing side. So according to the Pythagoras theorem, in the right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. In the right triangle PHQ, the hypotenuse is PQ, therefore the square of the hypotenuse is PQ square, and it must be equal to PH square plus HQ square. PQ is 8 plus R, therefore PQ square is 8 plus R square, and it must be equal to PH square. PH is 8 minus R, therefore PH square is 8 minus R square plus HQ square. HQ is the missing side, so we leave this as it is. So according to equation 1, we actually found out that 8 plus R square equals to 8 minus R square plus HQ square. Here, open the brackets on both sides of this equation, equation 1, and find out that according to this equation, equation 1, 8 plus R square equals to 8 squared, that is 64, plus R square, plus 2 times 8 times R, 2 times 8 is 16, and times R is 16R. So in this side of equation 1, we have 64 plus R square plus 16R. In the other side of equation 1, we have 8 minus R square. 8 minus R square equals to 8 squared, that is 64, plus R square, minus 2 times 8, that is minus 16, times R, so it is minus 16R, plus HQ square. Here we have 64 on both sides of this equation, equation 1. So so 64 we get cancelled, and we have R square on both sides of this equation, equation 1. So R square we get cancelled. So what is left from this equation, equation 1, after we cancel those two expressions? What is left is that in this side of equation 1 we left only with 16R. On the other side of this equation 1, we left only with minus 16 plus h square. So according to equation 1, we actually found out that 16R equals to minus 16R plus HQ square. Here we added 16R to this equation, equation 1. If I found out that according to this equation 1, 16R plus 16R is 32R, so 32R equals to HQ square. Here we took a root out of this equation, but before that we substituted 32 by 16 times 2. So 16 times 2R equals to HQ square. Here we took a root out of this equation, equation 1, and found out that according to this equation, equation 1, HQ equals to the square root of 16, that is 4, times square root of 2R. So inside the root, we left only with 2R. In conclusion, we actually found out that HQ equals to 4 times square root of 2R. Here, this is actually side HQ, that is equals to 4 times square root of 2R. We already found out that the quadrilateral HQMO is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. So in rectangle HQMO, side HQ must be equal to the opposite side MO. But HQ equals to 4 times square root of 2R, therefore MO must be also equal to 4 times square root of 2R. So in the drawing we have this small circle touches the big quarter circle at point T. That is to say, the small circle an internal notch with the big quarter circle, and whenever you have an internal notch between two circles, you can implement rule 9. On page quickly of rule 9, according to rule 9, if two circles touch each other internally, then the straight line that connects their centers together passes through their touching points. So here we have this big circle. The center of this big circle is 0.0. We have this small circle. The center of this small circle is 0.m. And the big circle, the small circle touch each other internally at point P. So there is a range between them at point P. And according to this rule 9, the straight line that connects the centers together, that is to say the straight line OM, must pass through point P, that is their touching point. Again, the straight line OM must pass through point P, that is their touching point. Or OMP is one straight line. Again, OMP is one straight line according to rule 9. We can definitely implement rule 9 in our drawing. In our drawing, we have this small circle touches the big quarter circle at point T. So they have an internal notch between them at point T. Therefore, according to rule 9, we know that the center of the quarter circle is here at point O. The center of this small circle is here at point Q. And according to rule 9, the straight line that connects the centers together is the straight line OQ, of course. So the straight line OQ must pass through point T. Again, the straight line OQ must pass through point T, that is their touching point. Or OQT is one straight line. Again, OQT is one straight line. So if OQT is one straight line, it means that OT is one straight line. So OT is a straight line, but what is the definition of the straight line OT? The straight line OT starts from point O, that is the center of the quarter circle, and that's at point T, that is the point of the quarter circle itself. So this is exactly the definition of a radius. Therefore, OT is the radius of this quarter circle, that is equal to 16 units in its length. Here OT equals to 16. What is the definition of line segment QT? Line segment QT starts from point Q, that is the center of the small circle, and that's at point T, that is the point of the small circle itself. So this is exactly the definition of a radius. Therefore, QT is the radius of the small circle, that is equal to R. And therefore, what is the length of line segment QO or OQ? OQ equals to OT minus QT. Again, OQ equals to OT minus QT. Again, OQ equals to OT minus QT. So OQ equals to OT, that is 16, minus QT, that is R. So in total, OQ equals to 16 minus R units in its length. In the next step, I copied the blue right triangle OQM in a new page and implemented the Pythagoras theorem on this right blue triangle OQM. This is the right triangle OQM, the right blue triangle OQM that I copied from the original domain. We just right now found out that the opponent QO equals to 16 minus R, QM equals to R, according to what is given in the question. It is the radius of the small circle, and side OM equals to 4 times root of 2R. So according to the Pythagoras theorem, in this right triangle OQM, OQ square equals to OQM square plus OM square. Again, OQ square equals to QM square plus OM square. So OQ, that is OQ square, that is the square of the hypotenuse. We know that OQ equals to 16 minus R, therefore OQ square is 16 minus R square. And it is equal to QM square. QM is R, therefore QM square is R square plus OM square. OM is 4 times square root of 2R, therefore OM square is 4 times square root of 2R square. We open the brackets on both sides of this equation and equation 2, and finally found out that the running to this equation and equation 2, 16 minus R square equals to 16 square, that is 256, plus R square, minus 2 times 16, that is minus 32 times R, so it is minus 32R equals to R square, and 4 times square root of 2R square equals to 4 square, that is 16, and square root of 2R square equals to 2R, because the power cancels the root and you left only with 2R. So in total, this expression equals to 16 times 2R. So according to equation 2, if we found out that 256 plus R square minus 32R equals to R square, and 16 times 2R is 32R. So here we have r square on both sides of this equation, equation 2. So r square will get cancelled. After we cancel r square, on this side of equation 2 we left only with 256 comes 42r, and the other side of equation 2 we left only with 32r. So if we move according to equation 2, we should find out that 256 comes 42r equals to 42r. Here we add 32r to this equation, equation 2, and we found out that 256 equals to 32r plus 32r, that is 64r. So according to equation 2, 256 equals to 64r. Here we divided this equation, equation 2, by 64, and finally found out that r, that is the radius of this small circle, the radius that we are looking for, equals to 256 over 64 is r, and it's 4. 256 over 64 is 4. So we found out that the radius of this small circle r equals to 4 units in its length. Okay, thank you very much.